So, let's do some work. Today's talk is called With Eyes Wide Open. And for the last few years, I've been lecturing science outreach and science communication to young people. And one of the main rules is know your audience. And as I was preparing this talk to you, I realized that I know nothing about you. In fact, when I was preparing it, I realized that I know nothing about Bulgaria or Bulgarian people and your culture. So I start guessing that, okay, how can I know something about you? Because at this stage, you are something like this to me. Okay? Just a bunch of people, and I know nothing about you well. One thing I know, you are interested in science, and at least you are curious in science. Okay? But I must confess that in my mind, I would like very much for your audience, my audience, to be like this, like a pop rock concert, and hopefully in a couple of years, we'll have this room full of people just shouting and yelling and woo! Stadium full of people just going crazy about science. We'll get there, I'm sure. But for now, it's nothing like this, and I know nothing about you. In fact, I tried to rehearse one sentence in Bulgarian. Okay, be nice with me. Удоволствие да съм тук. Yeah? Okay. Okay, I have the translation, but okay. So, but wouldn't it be amazing if just by looking at you 1,000th of a second, I could know your names, your jobs, how do you relate to each other, your dreams, your aspirations? Okay, probably a bit creepy, but that's something astronomers do. We are looking at the sky just for about 400 years now with some telescopes, and we know a lot. There is still yet to discover, but the main idea I want to give you is that almost everything we know, almost everything we know is from the light we see. We can't go there, okay? Of course, we explored the solar system. We even got to middle way in the solar system. We can go to the sun, but we can't go to the next, the closest star from the sun. It's not like I can take a black hole and a binary star and put it in a tube and mix it up and see what happens. We have no experimental knowledge. So it's the most important thing is to look at what we see and see big, okay? So nature provided many solutions for eyes, okay? For those of you who are a bit more distracted, the human eye is that one over there, okay? Nature provided many different forms of eye, but humankind developed a more efficient eye. So here we have one of the biggest eyes we have in the Earth. It's called Very Large Telescope. In fact, it's a group of 4 telescopes that can operate together or separately. And this is a beautiful picture of the Milky Way, but we have different eyes. We'll have the extremely large telescope. This is not a real picture. This is a mock-up, okay? This is in project. It's in construction. The mirror will have 38 meters wide, will be 38 meters wide, and it is a big eye. As big is the eye, the more light we can see, the more we can learn, okay? Different set of eyes. This is our radio telescopes. This is a set of telescopes called ALMA, and this one is called SCA. It looks like a parabolic dish because it is a parabolic dish, okay? And I will explain later how come this is also a telescope. Okay, everyone knows this experiment, I guess. This is a picture of Sir Isaac Newton just picking up a beam of light and crossing it through a prism. Everyone can do this experiment. You can do with a piece of glass or with the old CD, the old DVD, okay? And what you see, it's what everyone knows, that's a rainbow over there, okay? This experiment is so famous that it was also a cover of a Pink Floyd record. I bring just a tiny bit. You'll see why later on. And this is the cover, and it goes like this, just a bit. It's called A Gig in the Sky. It's 50 years old. Okay, so what we see from light is the rainbow. We see white light, and we can split it into different colors, okay? But in the universe, the radiation, the light we see, has much more colors than simply the ones our human eye can see, okay? The group of all these colors, in science we call it wavelength, is called the electromagnetic spectrum. Don't worry, the terms are complicated, but they are not very important, okay? What I mean is, we can see just this tiny little bit of all the colors light has, okay? And humankind developed technology to explore all those colors. And most of you know them all. If you can see, here we have television waves, we have devices like our cell phones that communicate through this color here. We have microwaves in our kitchens, we have X-rays and high energy over there to all kinds of medical devices. The infrared, everyone knows, that's what I'm using right now to move the slides, okay? So the light is much more than simply what we see with our naked eye. Okay, so the story goes like this. We get some beam of light, it travels throughout space, and it reaches our atmosphere. So here we have the light, and strangely enough, it is filtered by our atmosphere. So in 1957, astronomers and physicists all around the world gathered and concluded the obvious. If we want to know more about the universe, we have to see more. And the only way we have to see more is to go up there. Because our atmosphere just enables us to see in this region, the optical, what we call the rainbow, and here in the radio window. This is to say that radio waves are transparent to our atmosphere, but what happens to all the colors? Okay? So the conclusion was very obvious because, okay, so if we can just see a tiny little bit down on Earth, we have to go up there. And that's how space race began. It was not a bellic motivation, it was the need to know more. In fact, it was the purpose to study the sun outside our atmosphere. So, for the past 20 or 30 years, we built some space telescopes. Here we have. There are lots of space telescopes with different eyes that see different colors. Probably the most famous one is Hubble, that looks at light in the visible part, and a little bit here and a little bit there. And more recently, the James Webb Space Telescope everyone is talking about. 30 years ago, when I was an aspiring astronomer, the Hubble images were the latest thing, and they were incredible. But today, when I look at the James Webb's, I just sigh, okay? Because they are really amazing. With the advent of space telescopes, we turn our vision of the universe from this is a picture of the Milky Way in the optical, in the visible, the light we can see with our own eyes, and we turned it into a very different vision Because right now, we can see like this. So these are really the eyes wide open, okay? We can see in all the colors. But this is not an aesthetic experience, because each color, each wavelength gives us a different kind of information about the same object. In this case, we have the Milky Way, seen, of course, in the optical, in all the colors we can now see. Okay, some beautiful pictures, just comparing the Hubble image with James Webb. It's not a fair comparison, because look at the size of the mirror of the Hubble and of James Webb Space Telescope. So the bigger the eye, the more light we get, the more information. So you can look at the detail of the same object, and it's impressive, the improvement made by James Webb Space Telescope. This is a picture of deep field. We'll get there later. This is a part of the Orion Nebula. And the Southern Ring Nebula, there is a binary system over there, which means there are a couple of stars orbiting each other at the center of the nebula. And just two more beautiful pictures, the Tarantula Nebula and the M74, the Ghost Galaxy, okay, the Phantom Galaxy. Okay, but now we have to be a bit more technical. So what we know about light, because all we get is light. What we know is some basic, simple facts. We know that light travels through space at a constant speed, and its speed is 300 kilometers per second, which means that the light that is reflected by the moon, as you know, the moon does not emit light, it reflects, it will take about 1.2 seconds to reach Earth. Because, in fact, the speed, the light speed, it's very big, but the distances are even bigger. If you go to the sun, if you look at the sun, the light will take about 8 minutes and 20 seconds to reach us. The light emitted by the surface of the sun will take 8 minutes to reach us. So what does this mean? This means that when I look at the sun, I'm not seeing it as it is right now, because the light we are seeing traveled 8 minutes. So we are looking at it as if the sun was 8 minutes ago. That's the picture I see. That's already an old picture, and you can say, oh, 8 minutes. What does it matter, 8 minutes? It does matter. And this is a very important trick, I must say, to astronomers, because we know that 8 minutes and 20 seconds is the time that took light to travel this distance, 150 million kilometers. We call it 1 AU, 1 astronomical unit, is the distance, the mean distance between the Earth and the Sun. So what I'm trying to tell you is I look at the sun and see it as it was 8 minutes ago. When I look at the closest star from us, Proxima Centauri, I'm looking and I'm seeing it as it was 4.25 years ago. I'm not looking at the present, I'm looking at the past. When I look at the center of the Milky Way, I'm seeing it as it was almost 80,000 years ago. When I look at the furthest galaxies, I'm not seeing like they are now. I'm seeing them as they were 13,000 million years ago. So when I look far, I'm looking far in time. Okay? So it's just like the first row, I'm seeing you like you are now. The last row, I'm seeing you like you were 1,000 of a thousand of a thousand of a second ago. Okay? And this is an amazing ability that astronomers do, because we can, in fact, look at the past. Okay, so let me just give you some more detail. The distance that light travels during 1 year, it's called 1 light year. be careful. 1 light year is not a measure of time. It's a measure of space. It's the distance light travels during 1 year. Okay, let's do some simple math. Don't be scared. Okay. So it means a lot. Okay? That's the distance light travels during 1 year. It's a lot. You can try to read that number. I leave it to you. So just let us put all together. We can see as far as 13,470 million light years. So very, very, very far, which means very, very, very long ago. This is, in fact, the early beginning of the universe. Let me tell you a story. In Portugal, we now have TDT. It's blah, 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 TV, digital signal, something like that, okay? But a decade ago, all we had was UHF analogic TV waves, okay? So the signal was analogic. We had an antenna, and when we tried to tune up our channel, we were used to see something like this, okay? I think most of you have seen something like this. We are trying to tune our favorite soap opera, okay? And all we saw was some kind of noise. Part of this noise is light, it's radiation from the early beginning of the universe. It's called cosmic background radiation. So when you thought it's nothing on, you are watching the early ages of the universe as it was a baby. Mind that this light was not created, was not produced inside the stars, because in that time there were no stars yet, as far as we know, okay? So it was called cosmic background radiation. This is, once again, the image from James Webb Space Telescope. It's called deep field. Every object in this picture, in this photography, except that one, is a galaxy. And this is a very tiny portion of the sky. How tiny it is. If you look at the sky, and you just point your pinky finger like this image will represent 1/20th of your pinky finger, okay? This is how tiny a portion of the night sky it is. And still, it has thousands of galaxies, okay? Each galaxy, okay, just to remind you, 1/20th of your pinky finger extended like that. And you maybe think, yeah, but my arm is bigger than, it doesn't matter, okay? Because you are taller, your arm is bigger, your pinky is bigger, and everything goes right, okay? What I'm trying to say is, okay, don't do this, okay? You won't see anything, okay? Don't do this. If we get back, and if we pinpointed each galaxy we see, this is not a photography, this is a map, we get this structure. This is a mega structure. This square over here is 400 million light years across. And each point, each bright point, I'm not referring to that big blob. No, each pink point stands for a galaxy. This is the mega structure of the universe. And what you see is filaments with galaxies and some blobs with, okay, let's call it void. It's not void, okay? So cosmos, the universe, has a specific structure. The visible universe has a specific structure, and it looks like this. Okay, each bright point, it's a galaxy. Each galaxy, maybe it can have hundreds of millions of stars. Each star, it may have 2 to 4 to 5 to 10 planets around it. And I know what you are thinking. Oh, life. Where is there life? Is there intelligent life outside the Earth? Of course not. Because the main reason there is no intelligent life is that they didn't ever contact us. So that's okay. It's the main reason there is no. I'm joking. We'll talk about it later. So each star with some few planets around it. Is there life? I think you'll have a beautiful talk today, later on, about exoplanets, I think. Imagine this is the light you get from a star. Okay? If I can't do like this. But if some object crosses the light, you sense a decrease of the light. Okay? Simply, you have that experience. When you are out in the park and the sun is over you, when some cloud goes by, the light decreases. The bright of the sun decreases. Okay? The same happens with all the stars. Suddenly, if you get an object going in front of it, its bright decreases. So, light is not only important because we can see it, light is important because we can't see it, or we can see it with a slight decrease of its bright. If the object comes around once again, we start to think, whoa, is this the same object it crosses 3 months ago? Could it be? Could it be a planet orbiting another star? And this was one of the earliest techniques to detect exoplanets. It's not the only technique. And in fact, in the early days, we could obviously just detect big planets very close to stars. Because that's how we only had the technology to measure very high dips in this light curve. Today, we can detect very small peaks, therefore smaller planets, orbiting far from its star. And of course, this leads us to imaginate things. Okay? We have strong candidates. This is an artistic impression about almost the 2,000 exoplanets we discovered till now. But this is not a photograph. It's an artistic impression. And we have some strong candidates. Okay, mind something important. When you hear some astronomers saying, we detected an exoplanet, which means a planet orbiting another star in the habitable zone, this does not mean that there is life there. Okay? A quick example. In our solar system, we have 3 planets orbiting the sun in the habitable zone. But only one has life, Earth. Okay? As far as we know, of course. So, what does it mean, habitable zone? It means that the planet is at a distance that may provide the condition for having liquid water. So, it does not mean life. And when I ask my fellow colleagues that work on exoplanets, I ask, but okay, so life, the main building of life as we know it is water, but couldn't it be some different life forms? Of course, they say. But if we start looking at that condition that we know. Okay, so it's a fair answer. Okay, it's a fair answer. Here we have the candidates. Let us take not the most probable candidate, the strongest candidate. Let us take the closest one. Here, Proxima Centauri b. It's very close to us. It's 4.2 light years away. So we imagine that we want to go there. We take a couple and a couple of kids. We put them in a rocket ship, in our fastest rocket ship, and we send them to Proxima Centauri b, okay? Which is okay? A lot. So here we have our rocket ship, an amazing rocket ship, and here they go. The kid is smashed here. okay? And it would take more or less 90,000 years to get there. So forget science fiction, forget cryogenics, because it's the time it would take just to send a couple with a couple of kids. Okay, so imagine that travel. Dad, are we there yet? Dad, are we there yet? You ask the same thing every century. Okay, no one can survive this kind of travel, this kind of journey. Okay, so we can't go to the closest planet we know. We can't go. Not with the present technology, okay? But, of course, we can send some signal. Okay, let us take a kind of phone and send a signal. And this time, we'll send a signal to the strongest candidate to have liquid water. It's called HD 358, I think. This is a real picture of the planet, okay? And here is our emitter, okay? And we send a signal. In particular, this planet is 300 light years away, which means that light will take 300 years to get there. Okay? So, let us picture this. We pick up the phone, and we say, hello. And this hello will take 300 light years. Will take 300 years to get there. Okay? Meanwhile, I'm teaching my children and my grandchildren, my grandchildren's grandchildren's grandchildren's, and say, okay, mind that we are waiting for an answer. Okay, we are waiting for someone to respond to my question. Be aware, 300 years. And in some wild guess that there is a species, an intelligent species that can understand our message, that can decode our message, that is interested in sending back an answer. Okay, a wild, wild guess. Their answer would take 300 more years to get here. In the meanwhile, we teach our grandchildren and in children's generations after, okay, just mind, we are waiting for And of course, science evolves with failure, okay? And the most probable answer will be that one. Sorry, wrong number. So what I'm trying to tell you is universe is big enough. It's too big for the humankind's scale, okay? By now, our technology does not provide us the possibility to get in touch with another possible, remotely sentient, intelligent species, okay? Okay, but I want to tell you a different story now, because I'm still centered in the light we get. And I want to tell you the little light package journey, okay? In science, we call a tiny part of light, we call it a photon, okay? It's a little package of light. And most of this light is created inside the stars. Okay? Nowadays, in our universe, the light is created inside the stars. So let us take the sun as an example. It's the closest one, the one we know more about. And the stars are mostly hydrogen. Okay? A giant ball of hydrogen in a very different state. It's not liquid. It's not gaseous, it's kind of, what matters is that plasma is a very, very hot gas with electrical charge. Don't worry, we don't need this to understand what follows. So, our sun has an internal structure, as other stars have. In particular for the sun, we have 3 layers. The core, highly dense, look at the temperature, nice and warm, okay? Upwards, we have the radiative zone, which is very crowded with trillions and trillions of tons of hydrogen. And upwards, just close to the surface, we have the convective zone. These are very pompous names, I know. But I will explain it to you very simply, okay? And we can talk a little bit more afterwards. So, where are the photons created? In the core, okay? So, here we have the three layers. The blue one is the core, where we have hydrogen with high temperatures, with gigantic pressures, which mean that, in fact, we don't have hydrogen atoms. We have like a soup of protons and electrons all mixed up, okay? Something like this, okay? Just moving around. We have protons in green, we have electrons in white, something like that, okay? And they are smashed, completely smashed, because when we have mass, we have gravity. And gravity has this idea of pulling everything inwards, okay? And it smashes everything. So the hydrogen atoms, this soup, they will collide because they are smashed into each other. They will collide, they will release energy, and we will have an helium nucleus as a product. So, but the most important thing is, this is how energy is created inside the stars. They are nuclear fusion reactions, not fission as in nuclear plants. They are fusion, okay? We fuse the hydrogen atoms, we turn them into helium, and then we release energy. And this is the most important fact for the star's life. Because gravity is pulling everything inwards, and this energy release counterbalances it, and it's pushing outwards. So this is the equilibrium that rules the life of the star, okay? So we have energy release, lots of nuclear fusion reactions, we turn hydrogen into helium, and here we have lots of energy release with lots of photons. Of course, nice and warm, but they want to get out. And they get to the layer called the radiative zone. I told you already that when the photons get to the radiative zone, they find themselves, well, not in a very nice crowd, they find themselves trying to go through trillions and trillions of tons of hydrogen. It would be a little bit like I'm trying to leave this room and 3,000 million people trying to get in. Okay, so the photon does what I call the polite approach. Okay, he wants to get out. The hydrogen are looking like this, okay? And he can use this approach. Excuse me, can you give me some room? Excuse me, can you give me some space? Excuse me, excuse me, excuse me. And little by little, with this panic face like this, okay, of course, photon does not have face, okay? It's an image. So, collision by collision, the photon will do its journey. It's a very slow journey, and it is a kind of erratic trajectory, okay, because it collides here, 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 and we estimate that this journey will take 400,000 years. And of course, it will lose energy. For each collision, our photon will lose energy. So what happens when he cannot progress anymore? He gets to the upper layer of the star, in this case of the sun, and he cannot travel anymore because it has no energy to go through. And what it happens is, the photons arrive at the bottom part of the convection zone. I will explain to you later why it's called convection. Okay? And they stay over here. Okay, once again, soup, probably because we are close to the lunchtime, but what the soup has to do with convection zone? Okay. When we have a bowl of soup that is hot, in Portugal we have two schools of thought. There are kind of two main philosophy trends, okay? One say we blow, the other say we mix, okay? And in physics, the phenomenon is pretty much the same. So what happens when we take a spoon and we mix it? We are just mixing the hotter layers of soup that are here with the colder layers of soup that are over here. So we are mixing them up. So we cool the hotter ones and we increase the temperature of the cooler ones. So we promote the cooling of the soup. With the blowing up, we take a piece of soup and we just blow away the hot air that is here, and we replace it by cool air, promoting once again the cooling down of the soup. This is called forced convection. Okay? But in the sun, we don't have a giant spoon over there, just like mixing the layers of plasma. Okay? So what happens is this. The photons arrive, they cannot progrede, so they start heating up this part of the plasma. And exactly like a hot air balloon rises, this piece of plasma, because it's hotter, it gets less dense, and it starts rising. Okay? Exactly like a hot air balloon. So it starts rising. As it rises, it cools down. As it cools down, it gets denser. As it gets denser, it goes down. As it goes down, it gets warmer. As it gets warmer, it gets less dense. It goes up, it cools down, it gets denser. And as it gets denser, it took me 1 day to rehearse this choreography, and you don't seem impressed. So this is the convection, okay? That's what we called convection. And we have the convection cell. This is a more efficient process to transport energy, and will take a few weeks from energy to go from here to the surface. And we can even see it. As we look at the solar surface, these are not in real time, these are movies. Okay, this is called granulation, and this in fact is the top part of the convection cells. Okay, when we look at the sun, we can see the top part of the convection cells. So the plasma is rising, and that's what I see. And I think we can see the bubbles moving around, okay? So this is not in real time, okay? But the sensation is we are watching boiling water. It's not water, okay? It's plasma, and we see the top part of the convection zone. Okay, so this is how the little package of light travels. I'm just wrapping it up. When the energy gets to the solar surface, we still can see this. These are time-lapse photography from a colleague of mine called Miguel Claro. This is ground photography, so with instruments from ground, not from space. And I just want to show you a little bit. Oh, okay, here it is. So, here is the solar surface, and this is plasma all around that is ejected from the solar surface, okay? So plasma goes up and goes down, not by convection, by a different kind of phenomena that relates with magnetic field, another different story, maybe for next year's science festival, okay? These are beautiful pictures, and which means that the energy that gets to the surface still has to cross all these kind of clouds and solar atmosphere with plasma all around. Okay? So here we have our photons, very different from the ones that were created inside the star, and we still have to go by that plasma clouds over there. Therefore, still, mind that the photons were created 400,000 years ago inside the star. Okay? So, they reach the solar surface, and finally, they will travel 8 minutes and 20 seconds to reach us. And once again, here we have a human eye, and once again, we do the same experiment Newton did, with much more sophisticated apparatus, of course. And when we look at the rainbow, once again, we see something like this. And the obvious question is, I guess, who stole the colors of the rainbow? Because, as you can see, there are a lot of dark lines over here. So, going back to Pink Floyd's theme, it's something like this. Someone stole tiny little bits of the rainbow. And I guess you already know the answer, or at least part of it, because you know that, from the early beginning of my presentation, our atmosphere filters the light we get. But it's much more interesting, because the light we get from the surface, it has some black lines over here that were filtered by specific components of our atmosphere. Mainly ozone, that filters the ultraviolet, but of course the molecular oxygen, water, and also CO2. So when you look at the light of the sun, we get down here, you can comprehend, you can understand the composition of our atmosphere. But more than that, because you can also get other different lines that represent the material, the plasma, that the light crossed on the surface of the sun. It gives us valuable information about part of the composition of the sun. This is called the metallicity of the star. It's so much important for life as we know it. I don't have time to tell you about that beautiful story, but mind that metallicity is a very important part of a star. So, what I'm trying to tell you, I just will take you 2 or 3 more minutes. What I'm trying to tell you is that the light we get from a star has all this kind of information referring not only to the features of the star, of the light that is produced, but also the journey, the travel it made from the star to us. When you look at the rainbow, at the electromagnetic spectrum of 2 of these stars, Betelgeuse and Rigel, we can see that the rainbows are quite different, okay, in intensity, and the dark lines are very different one from another, which means that each star has its own signature. This spectrum is a signature of the star and tell us an incredible story, okay, about its temperature, its size, its distance, its composition, its metallicity. Okay, there are many different stars, just looking at sizes and surface colors. Here we have Betelgeuse, I told you about. It's a very big star. Here we have UY Scuti, it's bigger even. So where's the sun? That tiny little spot over there is our sun. So how big is this star over here? If I take this star and put it in the same place where the sun is, in our solar system, just imagine if we could do that, it would, okay, that's the sun. We could see that it has a radius of 8 astronomical units, which means that if I put the star in the center of the solar system, where is the sun, it would reach Jupiter's orbit. Okay? Earth would be inside of that star. Look at this representation of the solar system. The distances are not in scale, the sizes are not in scale. What matters to me, it's the representation. Okay? This is just a way to look at our solar system. And for many, many years, we had a very elaborate theories, nice ones, very highly grounded theories, that try to explain why we have the rocky, smaller planets closer to the sun and the gaseous giant ones further from the sun, okay? And we had some nice theories regarding solar system evolution, okay? But nowadays, with the exoplanets findings, we have all kinds of solar systems. Look, they are very different. It doesn't matter what this stands for. It's the same representation for many stellar systems we already know. They are quite different. So what I'm trying to tell you is that there's so much we still have to discover because we are improving every day. That's why we need those kids over here, okay, to join us and help us to discover new things. We have already 30 years of data to process. We need minds. We don't need just machines. We need minds, okay? It's very important. So by now, look, this is all kind of stuff we already know about stellar systems, very different ones from ours. So right now I look at you and I can see, I can know a little bit more, okay? Probably your names, not even your names, that's lots more to discover. Just to finish. Despite what many people think, science is not absolute. What we know for sure today will probably be incomplete or even wrong tomorrow morning, okay? So we are constantly learning and constantly learning new stuff that poses questions and that collides with the things we are sure to know that is not true. But that's what it's an incredible adventure, the adventure of knowledge. And this kind of festival, it's very important to try to develop some kind of scientific culture, because scientific culture is a part of culture, it's not a different parts, okay? Literature, poetry, all kinds of arts are as important as science, and it's a main building with all together. But the scientific method, it's what provides us critical thinking, and this is a very important part of citizenship, which to me is the other parallel face of democracy. So these kind of initiatives are so very important. So at last, I think you get to know a little bit more me. My name is Alешандре Айбео. Thank you for having me. Thank you for coming. It was a nice pleasure being with you. Thank you.
I'm starting work at a preschool, and I was really interested to know, from your experience, what's the youngest sort of student that you've spoken to? What activities have you done with them? I'll be teaching 3 to 7-year-olds, and I'd love to get them interested in space and the cosmos, but what can you do with them at a level that they'll understand at such a young age?
Okay. Do we have 60 minutes more to talk about it? The most difficult audience is that one. It's the most difficult audience you ever get, okay? When I started these things, a little bit, okay, I thought, okay, let's start with 12-year-old, 15 years old. No, we need to start when they are 3, okay? That's when we need to start with kids. They are natural curious, okay? So we just have to nurture that. What have I done with kids with those young ages? I can tell you lots of stories. I will tell you just one, okay? A long time ago, I did a presentation to 3-year-old, 3, 4, and 5. And that was exactly my question. What can I do? And I just took the video projector. On that time, it weighed 30 pounds or something. It was giant. And I just showed them nebula, just like that, telling them that we're maternity of stars, not explaining nothing else. And of course, their emotional reaction were like, oh, as mine it is nowadays, still today, I'm looking at this incredible picture of James Webb's, and I'm amazed, I'm still amazed. But stop there. Do something like that. As simple as it seems, you are telling them that stars are born, stars evolve, stars even die. Okay? Don't tell them that the star will die in 4.5 million years from now. They won't get that because we don't get that, okay? I have a traumatic experience with some kid with 3, okay. So that's enough, because afterwards they will do thousands of questions, and good luck with that. They will be the toughest questions you will ever answer. So it's very simple to move 3-year-olds, okay?
Amazing presentation. I have maybe a bit deeper question about the lacks and the small black spots in the rainbow.
Okay.
Maybe it's very deep, but aren't these spectral lines, basically?
Okay, what happens is we have light with all the colors. And as we go through some medium, it can be the plasma in the solar surface, or our atmosphere, or something else that light crosses, okay? The molecules the light crosses absorb part of that colors. And some of them even emit different light. Okay, just a fun fact. Tomatoes are bright red, okay? Why are they bright red? Because they emit in the infrared, okay? And we can see good enough the infrared, but we can see a bit. So that's why they are bright red, okay? So what happens is matter absorbs light, and it can also emit light. Everyone here is emitting light right now. But you are emitting light our eyes can't see. But if you take an infrared camera, everyone shines. Oh, that's a great album title for Rihanna or something like that. Okay? So that's the story light tells us. But I think it was not quite your question.
It was a bit more scientific question, but deeper. But I have another question, because I've read that actually the colors of the nebula, which we see, are not exactly the colors that they have. And is that true? Or?
In some cases they are true, okay? Because the pictures we see are a composite, okay, layer after layer. And sometimes astronomers do a little bit of shifting, okay, just for us to see, because we can't see the other wavelengths, the other colors, okay? Remind that each wavelength, each color, gives us a different information. The galaxy I showed you, the Phantom galaxy or something like that, had some very bright red dots. That means stellar formation, okay? That means stellar maternities all around. Still, the colors we see from nebula can see from absorption or can see from emission, okay? It even depends on the stars that are lying there. For instance, the Orion Nebula is a maternity of stars, and its colors depend on the light emitted on the stars that live inside of her, okay? You can come to me later, okay?
So I also have a question that I have actually had for a bit of a long time, and I can finally ask it to someone, which is very cool. I have a question about why do stars have different colors, And why do stars not have specific colors like green or purple or something like that?
Okay.
And does it have anything to do with the absorption of light from the plasma? Or yeah.
Okay. Yes and no. The simplest answer is color depends on temperature, on surface temperature. Our sun is yellow because its surface temperature is about 600 degrees. Okay? It does not mean that the inner layers of the sun are at 6,000 degrees. Okay? The top layer is at this temperature, and something we call the black body spectrum, doesn't matter, means that at that temperature, the peak, the highest peak of color emitted is around yellow. But this doesn't mean that the light we get is only yellow. We saw that is all kind of rainbow with dark lines, Summing them up, it gives us the yellow color. Okay? Different stars with different sizes in different stages of their lives have different surface temperatures. Okay? As hotter as it gets, the light gets bluer. Okay? Cooler stars get to the red part of light. Okay? So it's a bit the opposite way as hot water and...
the energy is in the convection zone. At the start of the convection zone, we have light that passes energy to the convection zone, and when it gets to the top, the energy converts back to light?
Yes.
Okay.
Okay, because as I answered the young girl behind you, matter absorbs and emits light.
Yes.
So the energy gets to the top of the convection zone, it emits light because it's hot,
yes,
and that radiation will travel through plasma and through space till it reaches. That's exactly that. So, but that's a part of your question I think I didn't answer. So, color and temperature are perfectly related. That's when you try to buy a light bulb, you have to look at the temperature to see if it's a warm light or a cold light. Okay? You can look at it and just choose it with the temperature scale. But you ask, why is there not any green star or purple star? Okay? Because the light emitted by that star, with a different peak depending on the temperature, summing all that up, it does not bring the mix like a green star.
You cannot have a blue and red star at the same time, so that you can get a green star.
Yes, okay. You can see that way, yes. Thank you once again. It was a great pleasure to be here. Благодарение. Being with you. Thank you.